So far, we've talked a lot about standard reduction potentials. Here, I want to make a distinction because we know that our standard reduction potentials are all measured at a hydrogen ion concentration of 1 molar, solute concentrations have to be 1 molar, pressure has to be 1 bar, and then you let the reaction attain equilibrium, and then you measure the voltages under those conditions. If you did that, then you will, whatever value you're going to measure is going to be indicated by this symbol E naught. Okay, so we already talked about that. But the thing to remember here is that when you deal with biological reactions, there is a problem with this defining standard conditions this way. Okay, so now the question is, what's the problem? The problem is this guy right here, the hydrogen ion concentration being 1 molar. If your hydrogen ion concentration is 1 molar, and if you want to talk in terms of pH, we know that pH can be calculated as pH is equal to negative log of hydrogen ion concentration. So if you substitute 1 molar here, the log of 1 is going to give you a pH of 0. And when your pH is 0, you are under very, very acidic conditions. We know that pH 7 is neutral. Anything above 7 is going to be basic. So we are at pH 0. So if you're going to measure these voltages for biological reactions at pH 0, it's not going to be very relevant because most of the physiological reactions happen at a pH of 7. Okay, so that means we need to redefine our pH conditions especially for biological reactions, because if you do them under any other pH conditions, then the values that you're measuring are not going to be very useful. And this is in fact what people have done, is that for the sake of biological reactions, they didn't do these standard reduction potential measurements at pH 0, but they measured these values at pH 7. Okay, and when they did that, they wanted to differentiate these values from the values that we measured at pH 0. So what they did is that they wanted to use sort of the same symbol. They still wanted to use E. They still wanted to use naught because it's standard reduction potential, but they added this little prime. So this is the prime symbol. This is the prime symbol. They attached a prime symbol to it to indicate that this E naught, whenever you see E naught prime, that is going to indicate that these are specifically for biological reactions, and it tells you that these values were measured at pH value of 7. And they did this, and then they created a table for a bunch of these biological compounds, and you can see here that those values are reported as E naught prime, and then those are also related, reported as voltage values, just like how we related, how we wrote down our E naught values. So there's no difference here. The only difference here is being that the hydrogen ion concentration was changed to pH 7. So when you change that, these voltages are going to shift, and you're going to end up with these values for these biological reactions. Okay, so that's something important to keep in mind. Another important thing to keep in mind is that when look at the way these reactions are written for biological reactions. Here, for example, it says pyruvate plus 2H plus 2 electrons gives you lactate, and it says that the voltage that is produced from that reaction is negative 0.185 volts. One of the biggest differences between this table and the table that we have seen before here is that in this table, you can see that all the chemical formulas are written out explicitly. So all the molecular formula, for example, water is written as 2H2O plus 2 electrons plus H2 plus OH minus. So this is written as a molecular formula of water, right? Whereas when you look over in this table that we're looking at, we can see that they're written as the names of the compound. The reason is biological compounds are usually pretty big. Their molecular formulas are going to be pretty complex, lots of atoms in there. So just by writing the molecular formula, we won't be able to tell which compound we're dealing with. So it's much more useful to actually write the names of the compound instead of writing the chemical formula of each of those compounds. Okay, so that's an important feature of when you deal with biochemical reactions. You're not going to see chemical formulas. You're just going to see the names of compound come up. If the compounds are simple enough, then you're going to see these formulas. For example, here, in the case of iron 3 plus electron going to iron 2 plus, it's written simply as the formula. But in the case of pyruvate, they're not showing the molecular formula of pyruvate. They just showed you the name of that compound and then indicated this value. Okay, so that's something important to remember about biochemical reactions. And this is the table for the standard reduction potential for biochemical reactions. Everything else that we talked about, how to figure out the net potential, how to figure out the delta G naught, how to figure out which reaction is undergoing oxidation, which reaction is undergoing reduction, what is my oxidizing agent, what's my reducing agent, all of those things are exactly the same as what we discussed for non-biochemical reactions. The only thing that's different for biochemical reactions is the values that we use. And instead of E naught values, we're going to be using E naught prime values. And that's the big distinction between non-biochemical reactions and biochemical reactions. All right, so we've done that. And now the question becomes, when we talk about biochemical compounds, what are those compounds that actually undergo oxidation reduction reactions? So these, when you talk about biochemical reactions, the substances that really undergo these redox reactions, majority of them are going to be coenzymes. Okay, they're going to be called compounds called coenzymes. What are coenzymes? Coenzymes are these organic molecules that are usually associated with enzymes, and then those molecules are the ones that are going to undergo oxidation reduction reaction. So for example, NAD plus is one such coenzyme, and that coenzyme is capable of accepting 2 electrons or losing 2 electrons, and it's able to undergo oxidation reduction reactions. So NADP plus is able to accept 2 electrons and it's going to undergo reduction reaction, and sometimes it can lose those 2 electrons and undergo oxidation reactions. So this is possible using these coenzyme molecules. So these coenzymes are part of enzymes, that is, they're associated with enzymes. These are organic molecules that are associated with enzymes, and those enzymes that perform oxidation reduction reactions, they have a name. The family of those enzymes have a name. The names of the family name is called oxidoreductases. Oxidoreductases are enzymes that are capable of performing oxidation reduction reactions. Okay, so there are a bunch of different coenzymes like these that are capable of doing oxidation reduction reactions in biochemical systems. Now, we have talked about chemical reactions that undergo oxidation reactions, then biochemical reactions that undergo oxidation reactions. Now the question is, how can we keep track of these reactions? What are experimental methods that we can use to know that there's oxidation reduction reactions? So one is, like, if you have a simple enough system like copper wire dipped in silver ion solution, which is the example that we went through, and you can see that we can see this color change very obviously. It's clearly telling you that this sort of change is happening. And if you want to be a little bit more precise, you can create 2 half cells and then connect them together, and then you can measure the voltage of those reactions, and then that will tell you that whether you have oxidation reduction happening there. Because if it's going to produce voltages, then that's going to tell you that there is something going on that is responsible for the production of voltages, and that's typically an oxidation reduction reaction. Okay, so these are some methods that we can use, but there's another method that we can use to, actually there's a bunch of other methods, and we're going to talk about one method that's really useful for checking whether oxidation reduction reaction is happening. Okay, so I'm going to give you an example. So here is a coenzyme NAD plus, and this coenzyme NAD plus is shown over here. So this whole structure that is shown here, this whole thing that is shown here is NAD plus. What is NAD plus? NAD plus is nicotinamide adenine dinucleotide. That's the full name. NAD plus is the observation, and you can see that it contains a positive charge here, so that's why we were calling this as NAD plus, this positive charge on the nitrogen. So what this NAD plus does is that when it undergoes biochemical reactions, it's capable of accepting 2 electrons and 2 protons, and NAD plus will change into NADH. Okay, so because NAD plus accepts 2 electrons, we know that any process that accepts 2 electrons is reduction. So NAD plus undergoes reduction to become NADH. Okay, how can we tell whether you have NAD plus in solution or NADH in solution? We can use what is called, UV visible spectroscopy. So we can use spectroscopic methods where the NAD plus, which is the orange line over here, you can see that that thing has no peak at 340 nanometers, whereas the blue guy here, which is the NADH, has a peak at 340 nanometers. So if you see an absorption feature at 340 nanometers, you can tell that, oh, now I have NADH present in solution instead of NAD plus. Because when we are learning all of these things and how to do these calculations, we also have to keep thinking about, if I were to go and do these reactions in the lab, how can I tell that these reactions are happening? For that, you have to use experimental methods to figure out what is happening. And UV visible spectroscopy is one such method. And there are so many other methods. You can use NMR, you can use, EPR, which is electron paramagnetic resonance. These two are pretty similar methods, but this one is useful for studying free radicals. And so this is a very useful method for that. So a bunch of spectroscopic methods can be used to study these oxidation reduction reaction. Here I gave you UV visible spectroscopy because this is one of the common methods that they probably teach you in your general chemistry level or your organic chemistry level. And this is something that's very commonly used. So I think it's something that's very easily relatable. So that's the reason why I've presented this method here. Okay. All right. So this is how we study we have methods to study oxidation reduction reactions. All right, so far we've spoken a lot about standard reduction potentials, and we've also spoken a lot about how to find out the net potentials using standard reduction potentials. But we have to actually understand why we need these standard reduction potentials and why we need to measure these net potentials based on standard reduction potentials. The reason why we're doing these calculations and things based on these standard reduction potentials is because you have a whole bunch of reactions whose reduction potentials are measured under a set of standard conditions. So any calculation that you're going to do based on that is going to allow for you to compare various kinds of reactions. So that's the main benefit of having these standard potentials and net potentials based on those standard reduction potentials. Okay, so the standard net potential, the net potential that we measured based on those standard reduction potential, we have always used this delta E naught as the way to indicate that. And the problem is that most reactions that we come across in nature, they don't occur under these standard conditions. They occur under non-standard conditions. They occur under very different conditions. So we have to be able to study them under how they occur naturally. Okay, and so that means that we should have a method to be able to calculate or to be able to obtain the net potentials from under these non-standard conditions. Those net potentials that we measure under non-standard conditions are going to be indicated by delta E without the naught on the top, right? Anytime you put the naught on the top, that tells you that it's measured under standard conditions, and that's what we have right here. But what I'm trying to tell you is that so far we were good at measuring all of these things. Now we need to find a way to figure out what this value is, delta E is, and not delta E naught. Okay, so how do we measure these potentials under non-standard conditions? Okay, so in order to do this, we're going to exploit some of the learning that we've had from other classes. Perhaps if you've taken your general chemistry 2, in your general chemistry 2, you may have come across this particular equation, which is delta G equals delta G naught plus RT ln Q. You must have come across this equation, and where this delta G over here is the free energy. We know that already delta G is free energy, so this is free energy, and it doesn't have a naught on the top. So that tells you that that's the free energy under non-standard conditions, Okay, this is the value under non-standard conditions. And this delta G naught over here is so again, I have to be very careful here. It's not just free energy, it's free energy change because it has a delta in the front. So this is free energy change. Same way, this delta G naught here is the free energy change under standard conditions. Okay, this is standard conditions. So this particular equation helps us connect free energy under non-standard conditions to free energy under standard conditions, plus this particular term RT ln Q. And we know that this Q is basically reaction quotient. And what is reaction quotient? Reaction quotient, we learned this when you learned your chemical equilibrium stuff, when you learned about equilibrium constant. So this reaction quotient is pretty much the same as the equilibrium constant. That is, we always write it as ratio of products over ratio of concentration of products over concentration of reactants, provided those product concentrations and reactant concentrations are values that you've taken under non-equilibrium conditions. Okay, so if you know what those numbers are under non-equilibrium conditions, if you took a ratio of that, we call that as reaction quotient. Okay, Now we're going to use this equation to come up with the equation that is going to be in terms of delta E's and delta E naughts, because that's the equation that's going to help us figure out what's the voltage output under non-standard conditions. Okay, so to achieve that, what we are going to do is use a trick that we've used before, which is we said before that if you want to convert your delta E naught value into delta G naught value, you have to use this equation. Delta G naught is negative NF delta E naught. We can, in the same way, use the same kind of relationship for delta G, which is the free energy under non-standard conditions. And we can say delta G equals negative NF, but instead of delta E naught, now it's going to be just delta E. This is the net potential of your reaction, net potential of the reaction under non-standard conditions, non-standard conditions. Okay, so this is the potential under non-standard conditions. So now what we are going to do is take this equation where we have expressed delta G in terms of delta E, and take this equation where we have expressed delta G naught in terms of delta E naught, and then plug it in to this particular equation. I'm going to plug this one here and then this one right over here in the place of delta G and delta G naught. When I do that, you can see that on this side I have negative NF delta E for the delta G term over here, and then negative NF delta E naught for the delta G naught term over here, plus RT ln Q. Now I'm going to simplify this by dividing the whole equation by negative NF. I'm going to divide on both sides by negative NF. When I divide it, you can see that I have negative NF, this term divided by negative NF, so I can cross this out, I can divide this term by negative NF, I can cross this out, but I'm left with RT over negative NF over here. So I can further simplify this. When I simplify this, this is how this equation is going to look like. And we're going to end up with delta E equals delta E naught. And because it's RT over negative NF, this negative sign goes from here to here. It replaces that positive sign. So we end up with RT over NF times ln of Q. This particular equation that we are writing down here is called the Nernst equation. And the Nernst equation allows us to figure out what is the value of net potential under a set of non-standard conditions. And this Nernst equation says the delta E naught that you measure under non-standard conditions is related to the delta, I have to repeat this again. So I should say the delta E that you measure under non-standard conditions is related to delta E naught that you measure under standard conditions, plus this concentration, or minus this term, which is dependent on this Q. This ln Q term is going to be the ratio of products over reactants. So that means what this is saying is your delta E, which is the value under non-standard condition, is related to something under standard conditions, minus this concentration term that involves your products and reactants. So that means your product and reactant concentrations are going to control what is the voltage output that you're going to get from your redox reaction. Okay, so that is pretty much the gist of how we measure our net potentials under non-standard conditions.